Welcome to Summarize Science, where we look at the cutting edge of cosmic discovery. Ever wonder if the Big Bang left a permanent mark on the universe that we can still see today? This paper explores how ripples in space-time from the very beginning of time, known as primordial gravitational waves, might be hidden in plain sight. Scientists are searching for these waves to understand the inflationary epoch, a moment of extreme expansion just after the universe began. While most researchers look for these waves in the light of the early universe, this study focuses on large-scale structures. Specifically, it looks at how matter is distributed, a concept called halo bias. The researchers explain that gravitational waves actually nudge matter around as it clumps together. This creates a specific pattern in the distribution of dark matter halos, which are the gravitational wells where galaxies eventually form. The interesting part is that these induced density changes are intrinsically non-Gaussian. In simple terms, it means the matter doesn't just spread out randomly like a standard bell curve. Instead, because the gravitational waves act on matter at a second-order level, they force it to bunch up in a very unique and predictable way. The paper describes a mathematical framework to calculate exactly how much this effect changes the clustering of galaxies. On page 3, the researchers evaluate these effects numerically using current cosmological models. They used a specific model called a Gaussian bump to represent the energy of those early gravitational waves. By doing this, they could predict how the halo bias would look for different masses of galaxy clusters at different points in time. One of the most exciting findings involves very old, high redshift halos from when the universe was quite young. For the rare and distant galaxies currently being studied by the James Webb Space Telescope, this effect could be very large. In fact, for halos at a redshift of 7, the signal is strong enough to be a primary focus for future observations. The researchers plotted these predictions on page 4 to compare them with other standard theories. They found that the signature left by gravitational waves is distinct and doesn't look like any other known patterns in the universe. This is a big deal because it means we have a brand new way to detect the remnants of the Big Bang. Instead of needing massive, specialized gravity wave detectors, we might just need to map where galaxies are located. The charts show that while the effect is small for nearby, massive galaxy clusters, it grows significantly as we look further back in time. This provides a complementary window into the very first moments of our existence. To recap, researchers have shown that the Big Bang's gravity waves leave a unique fingerprint on how matter clumps together. This halo bias effect is a sensitive probe that could tell us the energy scale of the universe's earliest expansion. While it is a subtle effect for local galaxies, it becomes a major signal for the most distant objects we can see with telescopes like JWST. In the future, this could help scientists distinguish between different theories of how the universe was born. It turns out the skeleton of our universe is carrying a message from the beginning of time. Thank you for watching Summarize Science, and stay curious about the wonders of our cosmos.